Hello everyone, this is Dr. Lennon, and in this section we want to look at integration by parts. So what we want to think of for integration by parts is kind of the product rule for the derivative backwards. So let's recall that. Recall if u and v are differentiable functions of x, then the way you take the derivative of u times v is you get the derivative of u times v plus u times the derivative of v. Now let's suppose we integrated both sides. Well, if you integrated the left, you would have uv, and on the right you would have the integral of u prime v plus uv prime dx. So up here this is the product rule for the derivative, and this is integrating both sides. With respect to x. So the thing is, what we can do is we can split apart that the right hand side is two integrals, so we can write it as the integral of u prime v dx plus the integral of uv prime dx. And what we want to do is we want to basically subtract one of these integrals and move it to the other side. So we have uv minus, we're going to subtract the second integral, minus the integral of uv prime dx, and this is going to equal the integral of u prime v dx. Now this might seem very mysterious, but it's actually very clever what we've done. What happens is we kind of look at the v prime dx, and we're going to call this dv, and we look at the u prime dx. So if we look at this integral, we're going to say u prime dx is equal to du. Okay, so we've got these two associations, and this is what gives the integration by parts formula. So the integration by parts, if we want to integrate a product of two functions, we say, suppose, again, u and v are differentiable, then the way we integrate u dv is, if you look above, it's just uv minus the integral of v times du. So this is the integration by parts formula. So let's have a look at some examples where we apply this formula to products of functions. We don't have basic antiderivative rules for, say, a polynomial times an exponential, so why don't we start there? Let's say we want to compute the indefinite integral of 14x times e to the 2x dx. Well, basically the setup is we say, okay, let's call u 14x, and dv we will call e to the 2x, and you can throw the dx in there if you want. So the first question is maybe, why did I pick u to be 14x, and why did I not pick u to be e to the 2x? Well, kind of the reason is when you take the derivative of a polynomial, you reduce it by a degree, and the basic antiderivative rule of e to the 2x is only going to be different by a constant. In general, it's going to take some practice for you to understand which one to pick, and a lot of times you can just play around and try one method, and if you pick wrong, just go back and switch. You might not be getting anywhere, and that's fine. Not everyone is going to guess correctly each time. So the thing is, we take this u equation and we differentiate it implicitly with respect to x, so we get du is equal to 14 times dx. And the dv equation we integrate. So what's the antiderivative formula for e to the 2x? Well, that's e to the 2x divided by 2. And we don't really need to worry about the plus c until the very last step. So our integral, we're essentially ready to, that integral that we started with, the integral of 14x times e to the 2x, is really just now u times v, which is 14x times e to the 2x over 2, minus the simpler integral of v times du, which is just 14 times e to the 2x over 2 dx. So that is not going to be so hard to integrate. In fact, it's just 7x times e to the 2x minus the integral of 7e to the 2x dx, which will leave me with 7x e to the 2x minus 7 over 2 times e to the 2x, plus our constant for general integration. So that's it. That's antiderivative formula there. Let's go ahead and look at another one. Why don't we make it a definite integral just to see how that doesn't make too much difference. Just making sure, did I frame this one on? Yeah, so maybe we indicate that this is our work. All right, so let's look at an additional example where maybe we have a definite integral instead. So let's compute the integral from 1 to 2 of x to the 4th times the natural log of x. Now, which do we want to do here? Do we want to pick u to be x to the 4th, or do we want to pick the natural log? Well, at this point, probably you don't know the antiderivative of the natural log. But if you do, you know the derivative formula is much more complicated. So for this example, it makes more sense to choose u as the natural log of x and dv as x to the 4th. So that's what we're going to do. We have u is equal to the natural log of x, and we have dv is x to the 4th dx. So du will equal 1 over x dx, and v will be x to the 5th over 5. So basically what I'm going to do is I'm just going to compute my antiderivative till I have everything done, and then at the very end I'm going to add those limits of 1 and 2. So our integral becomes the integral, so uv, which is x to the 5th over 5, times the natural log of x, minus the integral of 1 over x times x to the 5th over 5 dx. And what is that going to leave us with? So I'm going to put it in parentheses now because I'm going to add those limits back in. X to the 5th over 5, natural log of x, minus, well, this integral here is just x to the 4th over 5, which is going to be x to the 5th over another copy of 5, so that'll be x to the 5th over 25, and we're going from 1 to 2, putting those limits back. So again, this is basically 3.156, plugging in the 2, and then minus negative 0.04, plugging that in, and that comes out to about 3.196. So that's the answer for the second one. If you ever want to check yourself, there's a nice internet calculator, desmos.com. So I have that open already. So it's just desmos.com. And there's lots of things you can do here. So if we want to check the value of an integral, you can actually just do that here. So if you type int, it gives you an integral, and we want to go from 1 to 2. Anytime you have an indefinite integral, you can always check it this way. And we're doing x to the 4th times the natural log of x times dx. And we get our answer of about 3.196. 196, which is what we got when we did it by hand just using a regular calculator. But a lot of times that's going to be a fast check if you end up trying to work with a fairly complicated antiderivative and you just want to make sure you're right. Even if you have a indefinite integral, you can always plug in some example limits and check your answer that way. So that's just a good thing to know. Okay, so let's go ahead and talk quickly about, well, maybe we talked about the natural log, so let's investigate that quickly. In fact, the natural log of x, as surprising as it may seem, we can find its antiderivative by using integration by parts. Well, you might say, well, there's only one factor. Well, we'll see how to do that. So let's go ahead and look at this example. So we'll say compute the integral of the natural log of x dx, and basically we could say hint, you see this given as exercises a lot, use integration by parts. So pretty exciting stuff. Let's go ahead and do that. So how do we use integration by parts? Well, we know how to differentiate natural log, so we'll call u the natural log of x. But what are we going to choose? What is it being multiplied by? Well, everything we can always think of as being multiplied by 1, so we'll just say dv is 1 times dx. So then du is 1 over x, and v is just x. Technically, du is 1 over x dx. So our integral, the integral of the natural log of x dx, is going to be u times v, which is x times the natural log of x, minus the integral of v times du. So v times uv minus the integral of v du. So now that's just x times 1 over x dx. And we have x natural log of x minus just the integral of 1 dx. And we know the integral of 1 is actually just x. So we get x natural log of x minus x. And that is the antiderivative. You can check that that is in fact the case by looking at x natural log of x minus x and differentiating it. And you'll notice you'll just use the product rule. So you'll get 1 times the natural log of x plus x plus x times 1 over x, which is 1, minus the derivative of x, which is 1. So you just end up with the natural log of x. So you can write that down if you want, but what I said is exactly how it comes out. So that's one you might want to commit to your memory banks. The integral of natural log of x is x natural log of x minus x. Or maybe you just remember that you use integration by parts and one of the factors is 1, and then it'll take you maybe 30 seconds to write it out. Okay, so let's continue with one that's maybe a little bit trickier, but is pretty cool. So it's a little bit of work. And then after that, we'll get into some other examples with maybe some trig functions and stuff. But I want to do one more with polynomials just because kind of those are our canonical examples, stuff involving polynomials. So this combines, in fact, the parts idea along with the substitution, use substitution that we've been spending so much time with. So let's compute the integral from 0 to 1 of x cubed over the square root of 4 plus x squared dx. Okay, so this is actually pretty interesting because the choice for u and dv is not so obvious. Why? Well, typically we would want to let u to be something like 4 plus x squared. But when you take the derivative of that u, you're going to be getting some factor in x. So that's tricky if you're just trying to do a substitution. So actually, in fact, what we can do is, so let me write down the trick. you want to think of this as a product of two functions. So we want to think of x cubed over the square root of 4 plus x squared as x squared times x over the square root of 4 plus x squared. Well, why? Well, it's really easy to take the derivative of x squared, and we know we can integrate x over the square root of 4 plus x squared using the technique of u substitution. So that's the trick. So let's go ahead and do that. So we let u equal x squared and dv equal x over the square root of 4 plus x squared. And again, it might be helpful for you to think of this as x times 4 plus x squared to the negative 1/2 power. It's up to you, however you want to do it. And then we have du is equal to 2x, and v is the integral of this thing. So I will go ahead and tell you what it is. So the integral actually just ends up being 4 plus x squared raised to the 1/2 power. So basically, you want to integrate dv using u substitution. So I'll say do this by u substitution. And I will leave it as an exercise to you. So we'll think of that as an exercise. So the exercise is the integral of x over the square root of 4 plus x squared dx is equal to this 4 plus x squared times raised to the 1/2. It's really not so bad. So now we can go ahead and do the integration by parts that we set out to do. So we end up getting x squared times the quantity 4 plus x squared to the 1/2 uv minus the integral of 2x times 4 plus x squared raised to the 1/2 times dx. And again, I will let you know that the second integral is also computed by u substitution. So maybe we should write exercise number 1 and exercise number 2. You need to compute the integral of 2x times 4 plus x squared to the 1/2. So we have those two exercises there. Anyway, once you do that, you'll know what the answer is because I'm going to write it down, but still good practice. So we get x squared times 4 plus x squared to the 1/2 minus 2/3 times 4 plus x squared to the 3/2. And again, our limit values are just 0 and 1. So I'll tell you, if you put each one in your calculator, you end up getting approximately negative 5.217 minus negative 5.333. And this is about 0.116. So that is our answer. Again, there's those two little sub exercises left, but Those are not too difficult U substitutions. Maybe we can go back and check that we actually got this answer correct in Desmos. Why don't we do that? So this one, our integral is from 0 to 1, and we were doing x cubed divided by the square root of 4 plus x squared. So 0.116, which is exactly what we got. So that's good evidence that our work in that problem was correct. Okay, so let's throw some trig into the mix. Let's do a couple more examples. So example, and we'll do a few here. I'm going to say find each antiderivative, or find each antiderivative. Yeah, that's fine. So let's look at the integral of x squared times the sine of 2x dx. So what should we pick here? I believe what we're going to do is we're going to again pick u to be x squared, and let's let dv be the sine of 2x dx. So du is 2x, and v, well, the antiderivative of sine is negative cosine. This is actually going to be a u substitution with u is equal to 2, so this is going to be minus cosine of 2x over 2. Again, this is via u sub with u equal to 2x. So our integral becomes uv, so we get minus x squared cosine of 2x over 2 minus the integral of v du. So that is actually going to be, so we have a negative here, and we're subtracting a negative, so that's actually going to be plus the integral. The 2's are going to cancel, so we'll just have x cosine of 2x dx. Okay, so what's going on now? Well, we haven't finished the integral because we still have a product of two functions, but it's not the worst thing ever because we started off with x squared times the integral of a trig function. Now we only have x times a trig function inside our integral. So what we're going to do is we're going to do parts again. So evaluate this guy by parts. Do by parts. So what are the parts there? We have u equals x, and dv equals the cosine of 2x. So du here is actually just equal to dx, and v is going to be equal to the sine of 2x over 2. So that's how we get the parts involved. So this integral, if we want to bring that down now, the minus x squared cosine 2x over 2, that first term, and then what are we going to do? We get plus uv, which is x sine of 2x over 2 minus the integral of v times du, which is just sine of 2x over 2 dx. And then we integrate there. So the integral of sine is again going to be minus cosine, and the parts is going to add another 2 to the denominator. So that's going to finish off our integral minus x squared cosine of 2x over 2 plus x sine of 2x over 2, and then the two negatives here are actually going to make this plus cosine 2x over 4. And we have to remember to add our plus c for integration, indefinite integral. Okay, so for the next one, let's try let's go ahead and try the integral of e to the x times the cosine of x dx. So let's see what's going on here. So maybe we want to pick this one. It doesn't really matter too much, I don't think, because the derivative and the antiderivative of e to the x is going to remain stable, whereas cosine is just going to bounce back and forth between, you know, sine, cosine, negative cosine, depending on whether we're differentiating and integrating. So let's go ahead and pick u to be e to the x and see if this works, and dv to be cosine of x dx. So we would get du is equal to e to the x, and we would get v is equal to the sine of x. So then this integral here, this integral of e to the x cosine of x dx is equal to uv, which is e to the x sine of x, minus the integral of v times du, which is e to the x sine of x dx. So the dx is here in this one as well. So then we have an integration by parts again. So let's say for this one we let so what I want to do is I want to let u be the sine this time, because if I do u as the sine, the derivative will be cosine. So go ahead and just watch what I'm going to do here, and maybe it'll seem mysterious why I'm switching, but you'll see in a second. If you go the other way, I think you'll include another negative, then you'll get some cancellation. It won't quite work out. So if you tried to do it the other way, you might end up with a failure, but this should work. So let's pick u to be e to the x and dv to be the sine of x. And maybe, I don't know, maybe I'm doing it wrong. Maybe I counted my negatives wrong. So let's see. So this may go wrong. If it does, that's okay. That's going to be instructive. So dv will be the sine of x dx, and we'll end up with u prime is equal to, or sorry, I'm using du. Du is going to be e to the x. And now v is going to be the cosine of x. So what we end up with here is e to the x sine of x minus, so we have this negative, and then we have uv, so that's e to the x cosine of x minus the integral of v du, which is e to the x cosine of x dx. And so my idea is to actually replace this whole integral with the capital letter I, a variable change, and then we'll go ahead and solve for I kind of in the backdoor method there. But the problem is when I distribute my negative here, I'm going to get plus this integral, and if I get I on this side and I on that side, they'll cancel. So that tells me I wasn't supposed to switch, and so I picked my u and my dv incorrectly for the second parts. That's okay. When that happens, you don't fret. You just erase everything, and you go back and you switch them around, and you do it again, and hopefully you get the correct answer doing it that time. So that is perfectly normal. Everybody messes up in integration by parts. You know, you can't guess right the first time every time. So let's pick u to be the sine of x. Oh no, maybe... Did I pick u to be the sine of x last time? I think I did. So... if I pick u to be e to the x and dv to be the sine of x the antiderivative of the sine of x is minus cosine of x, and du here is e to the x. So yeah, I know I picked it differently this time because I switched them, and now this time u is e to the x, the same as in the first integration. So what do we get? So now we get e to the x sine of x, just bringing that guy down, and then I'm subtracting uv, which is minus e to the x cosine x, minus the integral of v times du. So I get minus the integral of v times du. So I have another negative sign coming in here, so now it becomes a plus integral of e to the x cosine of x dx. All right. So we are hitting the home stride. So let me bring down also on the left-hand side that integral just so you see what's going on. So now we have the integral of e to the x cosine of x dx. And this is equal to e to the x sine of x. Distributing the negative, we get plus e to the x cosine of x. And then we get minus the integral of e to the x cosine of x dx. So it might seem like we didn't make any progress, but in all fact we did. So this quantity right here, if we call this capital I, it would be the same as this thing. Well, we can just replace this equation by I, and that's exactly what we're trying to solve for. So if you have I equals e to the x sine of x plus e to the x cosine of x minus I, we can just add I to both sides. And we're going to end up with 2I equals this e to the x sine of x plus e to the x cosine of x. So 2I equals e to the x sine of x plus e to the x cosine of x. Divide by 2. And now we found our integral that we wanted to. So we have e to the x sine of x over 2 plus e to the x cosine of x over 2 plus a constant for integration. I could have included that before, but if I divide it by 2, I can always replace it by c again, and it's if c is a general parameter, general constant, then so is c over 2. So it wouldn't make any difference. I could just relabel. So anyway, why don't we finish here with this example, and if you have any questions, please let me know, and I can go ahead and do some more on whichever ones are giving you problems. Otherwise, this is Dr. Lennon signing off.